error in wireless communication channel, and today we will be starting the block code. So one of the channel coding techniques, a simple channel coding techniques, but this is effective in case of your past error correction and also for your random error correction. Okay. So I am presenting the slides. Slides visible to you?
Yes, ma'am.
Okay. So this is our first coding techniques, channel coding techniques, block code. I think some of you already studied that thing, the block code. So maybe this is the repetition of that. So in case of block code, it's a linear code. And in all the coding techniques, we are considering the digital signal. Okay, signal is digital signal. So for digital signal, we are applying the coding techniques, encoding, encoder and the decoder, encoding at the transmitter section before transmission of information to combat error, and at the receiver section, we are decoding the information. And in case of your block code, already I have said there is a systematic addition of redundant bit and non-systematic addition of the redundant bit. Okay. So there is systematic block code and the non-systematic block code. So in case of block coding, so your information, suppose we are considering the information, long length of information. So it's a you are dividing your information into pieces, means you are dividing the information into packets, and each packet contains k number of information bits or k number of information digits. So each packet, in each packet you are adding the redundant bit, and your code length is n. K number of bits is your message bit, n minus k is your redundant bit. So it is called as a parity bit. Sometimes it is called as a parity. Generally we are considering this is the parity bit. So the encoder of the block code transfers a successive binary digit into longer block of n. Obviously, when you are adding the redundant bits, so the length of the code is increases. How much amount of code length is increases, that will be depends on how many number of redundant bits you are adding along with your information digit. So in this case, your information digit is k, n minus k parity bit you are adding, systematic addition here. So your how many parity bit you are adding? Now you are adding n minus k. So your length of code is n. So this code length is transmitted. After the coding technique, you transmit the information to the channel. So there is number of packets. That's why this second block is showing there are number of packets of information, because your whole information is divided into number of packets. And each packet contains a number of message bits. So this message bit we are denoting as M0, M1 up to MK, because K is the number of message digit or bits. So each message block contains K number of digit or bits, and we are termed as K tuple. this will be termed as K tuple. Okay. So the properties of when you are adding the redundant bit in for designing a coder, encoder along with your information, so you have to follow some rules. Okay, so in case of block code should, when you are designing the block code, so you have to follow some properties of the block code. What are the properties? First is the sum of the two code words belonging to the code is also a code word belonging to the code. That means, what does it mean? As if there is a set, suppose if I say there is a set S, and this set S contains number of subset S1, S2 up to Sn. Okay, so this S1 is a code word, S2 is also a code word, S3 is also a code word, up to Sn is also a code word. And the set S is a linear block code. So if I add S1 and S2, the sum, the resultant of this summation will give another code that should be within the set S. This is the property number 1. The sum of two code words belonging to the code is also a code word belonging to the code. So the after addition and after summation, the resulting code also belongs to this code S. If I say here set S also belonging to the set S. And the code contain the all zero word is always in the code word. So that means if I say S is a set and within the set S there is a subset S1, S2, S3 up to Sn. Within this your set, any of the code word, either S1 or the S2 up to Sn, this must be, the word must be contain all zero. So suppose if I say S1 and the length of the code, if I say 6, so the S1 should be 0, 0, 0, 0, 0, 0. Maybe S2 will be 0, 0, 0, 0, 0, 1. Like this. Okay. And the minimum distance between two code words of a linear code is equal to the minimum weight of the code. Already I have mentioned in our earlier classes what is the minimum, what is the called the weight, Hamming weight or Hamming distance. That thing already I have mentioned. So weight means in a code word how many non-zero elements are there. The minimum distance between two code words of a linear code is equal to the minimum weight of the code. So if I say S is a set and the set contains S1, S2, S3 up to Sn subset, then the distance between S1 and S2 or S2 and S3 or Sn minus 1 and Sn, so this distance, that is the minimum distance between the code word, is equal to the minimum weight of the code. Okay, so it may contain in a code a set S, the code word may be 0, 0, 0, 0 or 0, 0, 0, 1 or 0, 0, 0, 1, 0, like that up to your 1, 1, 1, 1, 1. So for that case, the what is the non-zero element in the code word? If I say that is the 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, So obviously the minimum weight will be 1 for this set S. Minimum weight of the code will be S. So if we satisfy, if a code you are designing and satisfies these 3 properties, then you can say this is a linear block code. And here the addition, that means the summation, when you are sum of 2 code, all the operations should be Galois field operation. This is the linear algebra. Okay. So it is not like that 1 plus 1 equal to 2. Okay, XOR operation. So 1 plus 1 equal to 0. 1 plus 0 equal to 1. 0 plus 1 equal to 1. 0 plus 0 equal to 0. Okay. These are the modulo 2 operation or Galois field 2 operation. Now, if I take an example, the properties will be much more clear. Suppose a linear block code with n equal to 4. That means after addition of the redundant bit, the code length that is generated is equal to length is equal to 4. And we are considering the code C. Already I have said that is the set S. So now you denote that set S is equal to set C. Okay. So C contain the subset or code word 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1. So the length of the each code word is 4. So you don't know how many redundant bit is added here. So this is already mentioned. The length is 4. So that's why the generated the code word is the 4 length, each of 4 length. Now this code, can I say this code is a linear block code or not? So you have to be check these 3 properties. Now if I check the first property, so we have to be add this code word with this code word. So if I add the first property, the sum of 2 code word, or this code word plus this code word, or this code word plus this code word. So sum of any 2 code word, sum of 2 code words. So now if I check 0, 0, 0, 0 with any of that, obviously it will be gives the code word that is belongs to that C. Because 0, 0, 0, 0, 0, 0, 0, 0, addition it will be 0, 0, 0. So this the sum of these 2 code word, when generate a code word, resultant code word, that is also belongs to C. So I am not checking 0, 0 with other code word. So obviously it will be belongs to that C. If I add any other code word, suppose you add 1, 0, 1, 0, means the second 1, 0, 1, 0 with 1, 1, 1, 1, 1. If I add 1, 0, 1, 1 with 1, 0, 1, 0 with last code word 1, 1, 1. So what is generate? It generate 1 plus 1, 0, 0 plus 1, 1, 1 plus 1, 0, and 0 plus 1 is 1. So you are getting 0, 1, 0, 1. So this is the also be a code word that is belongs to C. So you are adding 2 code word, that is second and the fourth, and it gives a summation will be gives a code word that is also belongs to the code word in the third code word. Similarly, if you check for other, suppose that is 0, 1, 0, 1 plus 1, 1, 1, 1. 0, 1, 0, 1 means third and the fourth. So 0 plus 1 is gives you 1. 1 plus 1, 0. 0 plus 1 is 1. 1 plus 1 is 0. So 1, 0, 1, 0. So also this is nothing but the second element of the C. isn't it? So the sum word, when you are summing all these things in this way, it also shows that all are is belong to the code C. So it is satisfy the first property. Now check the second property. The all zero word is always a code word. Yes, the first code word is a all zero. So it is also within C, isn't it? So these two properties are satisfied. So first property is also satisfied and the second property is satisfied. Now we are calculating the minimum distance between two code words. Now the third property is the distance calculation property. If I calculate the distance between the first code word with the second code word 0000 with 1010, so distance is 2 because differ in two position 2. Now distance between first and the third difference in 1 and 2. Now first and the fourth difference is 4. This way you are checking the distance and the distance is minimum distance is 2. Now you have to calculate what is the minimum weight of the code. Minimum weight of the code. In the code C, there are 4 code words 0000, 1010, 0101 and 1111. Out of these 4 code words, what should be the minimum weight? Now the minimum distance is 2 and the Hamming weight of non-zero code word is, see here, your Hamming weight will be, first is obviously there was no non-zero element 0000. So for 0000, no that is non-zero element. Second is distance, second Hamming weight is 2. Third is Hamming weight is also 2. And for the code word Hamming weight is 4. So minimum Hamming weight is 2. And also you have found that the minimum Hamming distance is also 2. So this third property is also satisfied. Minimum Hamming distance is equal to minimum Hamming weight. So the code C satisfies the third property. So the code C now satisfies the first property, second property as well as third property. So you can say this is a linear block code. So you have to be checked this way. Is the code is a linear block code or not? So when you are generating a block code, so you have to follow these rules to generate the linear block code. Now some nomenclature is used for the coding techniques. So if I say the NK block code, N is the after coding length and K is your message bits. So the redundancy is N minus K, code rate is K is the information bits divided by N, the length of the code. That means after code. So K is your message, N is the code length, code rate is K by N, redundancy is N minus K. So K bits of message form 2 to the power K possible message sequence called K tuple. So as in a packet there is a K number of message bits, so obviously 2 to the power K number of sequence will be generated, message sequence will be generated. So it will be called the K tuple. So there are 2 to the power K possible code word corresponding to the K number of message bits. Each packet has K number of message bits. Now, when you are designing the code, so that means the encoder, what is the function of the encoder? So encoder transform that K message digit into longer block of N code word digit. Now code word or code vector, this n code word or code vector, it is called the n tuple. N tuple, this is not from, this is from the space Vn of all n tuple. Okay, this is not from, this is from or created. So this n tuple created a space, vector space called, we are denoting by that vector space by Vn. Now encoding procedure assign to each of the 2 to the power k tuple one of the 2 to the power n tuples. So a block code represent 1-to-1 assignment. So mapping is 1-to-1 mapping. What does it mean? This line, that is the when you are encoding, so how many your message sequence are there? Each packet has k number of bits. So the number of message sequence will be 2 to the power k. So they are k tuples. Okay. Now, when you are code the information, that will be gives you n, length is n. So number of bits or number of digits of the code word after coding, it will be n digits. So it will be 2 to the power n number of sequences will be generated. Isn't it? So 2 to the power k sequence will be mapped uniquely out of the 2 to the power n your code word sequences. So obviously there will be some extra sequence because n is greater than your k. So extra code word sequence will be there. So this mapping, that is 2 to the power k to 2 to the power n, that should be the unique mapping technique. Representation will be unique, and this mapping can be accomplished via a lookup table. So this 2 to the power k message sequence you have to be stored. So when you are forming the lookup table and they are uniquely represented, 2 to the power k message sequence is uniquely represented into from the 2 to the power n message code word sequence. So 2 to the power k, if I say there is a 3 message bits, so 3 message bits means 2 to the power 3 means 8 message sequences will be there, and you are adding 1 parity bit to form a code word. So obviously your n equal to 4. So how many code word sequence? 2 to the power 4 equal to 16. But this 2 to the power 8, sorry, 2 to the power 3 means 8 message sequence can uniquely represented from the 2 to the power 4, that means 16. Out of 16, only 8 you are using to uniquely code the 8 message sequence. This thing is clear, and this should be stored in a lookup table. So this message, that means code word 000 will be represented as suppose after coding 0001. Code word 0001 will be represented after your coding. It will be represented as 01010, like that. So you have to be stored this way, and by using a lookup table, and you have to be stored this thing. Now if k is very, very high, storing the 2 to the power k code vector in a dictionary is prohibited for a large k. So this lookup table, maintenance of the lookup, this is, if I say 3 bits, so it's not a problem. If your message length is high, so obviously if it is 39, 2 to the power 39, how much lookup table you have to be stored? So it is your storing space is required, large number of storing space is required. So this is very important thing when you are code the information by using the block code. So obviously you can get rid of that using some other techniques. I am coming that thing. Now before going to that, we are considering the vector space. You know that I have already mentioned that n tuple form a space that is Vn, and it is called the vector space over the binary field of two element 0 and 1. Only we are considering the 0 and 1 element because it is a linear algebra and we are considering Galois-Field operation. And Galois-Field operation number 2. 2 means two elements, 0 and 1. The binary field has two operations, modulo two operations. What are the two operations? One is addition, another is multiplication. So the encoding and the decoding function involve the binary arithmetic operation of modulo 2. So this thing is shown here. This all of you know this operation. 0, 0 is 0, 1, 0 is 1, 0, 1 is 1, 1, 1 is 0. So this similar bit gives you the 1 and similar bits is gives you the 0. So of that, if I add U plus V would be V is a code word and U is another code word. How do you add? Now V1 will be added with U1, V2 will be added with U2, V will be added with UN. This way. This is the arithmetic operation. And also the multiplication. These two operations will be we are considering. So, but mostly here we are considering the scalar multiplication and the arithmetic addition. So multiplication is 0, 0 is 0, 1, 0 is 0, only 1, 1 will be 1. So scalar multiplication, if I say a scale factor A multiplied with the code vector, so it will be how it is multiplied. Each element of each digit of the code vector is multiplied by the scaling factor. So that is a V1, a V2 up to a Vn. If Vn number of digit, because after code you are generating the length is n, because we are considering nk block code. Now we are considering a vector space Vn. So n is equal to 4. Vector space Vn, n is equal to here 4. V4 means n equal to 4. So how many code word is possible? The 2 to the power 4. So it will be 0, 0, 0, 0, 0, 1, 2 up to 1, 1, 1, 1. Okay. So the addition is, if I say addition is 0, 1, 0, 1 with 1, 1, 1, 0. How we are adding? 0 is added with this, 1 is added with this one, 0 is added this, and 1 is added with this one. So it will be like that, and it will be gives you 1, 0, 1, 0. Now multiplication, some scalar thing is multiplied. So here the factor scalar as is a binary field of operation. So obviously either 1 or 0 scaling factor will be used. So if 1 is multiplied, so each digit will be multiplied with 1. 1 is multiplied with 1, comma 1 is multiplied with 0, comma 1 is multiplied with 1, comma 1 is multiplied with 0. So that will be gives you same thing 1, 0, 1, 0. Okay. So subspaces, already I have said the subspace, or that is your in terms of your set and subset like that. So a subset S of the vector space Vn is called a subspace if the following condition met. So if I say here your vector space is V4, within the V4, so this may be the subset, this may be subset, this may be subset. So all these are subset of V4 vector space. So the subset S of the vector space Vn is called a subspace. You cannot say all the that is the code within V4 space are subspace. They have to satisfy the properties. Properties number 1, the all zero vector is in S, and property number 2, the sum of any two vector in S is also in S. So this thing already, the properties, this thing is nothing but the properties of the linear block form. Now if I say the V0, the first element of the V4 space, 0, 0, 0, 0, and another element is taken, that is 0, 1, 0, 1, 0, 1, 0, 1. Another element taken is 1, 0, 1, 0, and V3 is 1, 1, 1, 1. And checking any of these two, here it is checking V1 with V2. If I add V1 with V2, so it will be generated 0 add with 1, that gives you 1. 1 added with 0 gives also 1. 0 added with 1 also 1, and 1 added with 0 also gives you 1. So the modulo operation is gives you 1, 1, 1, 1. So this is also in S. This code vector 1, 1, 1, 1 is also in S. And also if I say S is a subspace where S is a subspace where you are containing, that is V0, V1, V2 and V3, 4 code word vector. So S subspace that is satisfy the properties 0 property and the sum of any two vectors. So obviously this also be a that means this is a subspace because this thing is contained within the space Vn. Clear? So it is easy to verify that addition of any two vector in the subspace can only yield one of the other member of the subspace. Clear? A set of 2 to the power k n tuple is called linear block code if and only if it is a subspace of the vector space Vn of all n tuple. So these are the subspace because it is satisfy the properties of the that is the vector space, the property number 1 and the property number 2. This is nothing but the properties of the linear block. Now see this plot or picture shows that these small dots are showing number of your code word vector because you are adding redundant bit n minus k redundant bit adding with k, and your code word length is generated, length is n. So obviously n is greater than k. So these 2 to the power n are showing by small black dots. But all these black dots are not necessary to uniquely map by 2 to the power k message sequence. This circle shows that only this number of code words are taken from the large number of code word vector to map 2 to the power k message sequence. Clear? So now how you can choose this thing, which will be your how you are representing. That means your suppose 2 to the power 3, if I say 2 to the power 3 means 8 message sequence is mapped mapped from the 2 to the power 4 means 16 code word. So how you will be mapped? Which one will be discarded and which one will be taken for consideration? So this should be so choice should be follow some rules. So for coding efficiency by packing the VN space as many as code word as possible. That means you small amount of redundant bit you add to that means as we are considering, suppose 2 to the power 3, that means 3 message sequence is converted into 2 to the power 4, that means the length of code word is 4. That means each message sequence contains 3 bits and transform into the 4 bits of code word length. That means 1 bit redundant bit is adding. So here addition of the redundant bit is very less, just a single bit. Okay, so obviously 2 to the power 3 will be mapped into 2 to the power also k code word length from the 2 to the power n code word sequence. Clear? That means 8 message sequence is mapped into 8 code word sequence out of 16 code word sequence. Now, if I add extra 2 bit with 3 bits of message sequence, so that will be your 8 message sequence is mapped into 8 code word sequence out of 2 to the power 5, out of 32 code word sequence. So your redundancy is you are adding more. So here this is the first sentence that is saying that the coding efficiency should be such that you packed in such a way that you add less number of redundant bits. So you are not discarding too much of the code word sequences. And also the code word to be as far apart from one another as possible, so that even if the vector experience some corruption during transmission, they may still be correctly decoded. Means, if I say a code word of 1011 and another code word 1001 1011 and 1001, how many code length difference, how many position they differ? Only the single bit position differ. So distance is 1 here. Minimum distance between the code word is 1. So you choose the code word in such a way so the distance should be far apart. Otherwise, if a single digit is changes, so during transmission of the bit, so it may be that means one code word may be that means erroneously detected as another code word. So that's why when you are map 8 message sequence into 8 code word sequence out of 16 code word sequence, you choose in such a way, mapping should be such a way that the distance between the code word should not be such that means there should be distance should be much more far apart, so that during transmission, if any noise occurs, you can correctly detect that code word. Now already I have mentioned that 2 to the power k number of message sequence will be uniquely mapped into 2 to the power k number of code word sequence out of 2 to the power n number of code word sequence. And it will be follow a lookup table. They are uniquely assigned. So this you have to you have to be maintain a lookup table, and you have to be store the lookup table. Now in this case, we are considering the K is 3, so 8 message, and N is 6. That means 2 to the power 6. Okay. So out of 2 to the power 6, only how many you are taking? Only 8 you are taking. And how, in this case, one example is showing that message 000 is after coding, it is coded as 00000. To follow the linear block code, 0 code word should be in your code. So that is 0. Now the second message 100 is not map as 000001. It is, you can choose any of the code out of the first 16 code word sequence. So it is map into 110100. Okay. So this should have some, there is some rules to design this thing. Similarly, your 001 is map into 101001. 101 is map into 011101. 111 is map is 000111. Okay. So that means your this lookup table you have to be stored somewhere. Okay. Now this is looks like not that much of complex, because we are taking only message bit is 3. So 8 message easily you can store. Now how was the code word to message assignment chosen for this 6.3 code? A unique assignment for a particular NK code does not exist. However, neither there is a complete freedom of choice. I have said that out of the 2 to the power 6, 64 code word sequence, you are only selecting 8 code word sequence, and rest you are discarding. Okay, so you have a freedom to choose that 8 code word from the 64 code word, but it is not possible. This completely freedom is not there, because this should have to follow the properties of the linear block code. 00 vector should be there. Some of the any 2 code words should also be contained within your code word, and the minimum Hamming distance should be equal to minimum Hamming weight. So these 3 properties should be followed, and by following these 3 properties, you have to be choose the code word. Okay. And also, if your message bit is too high, so it is very difficult to store that thing, this lookup table. So to get rid of from this, or to reducing the complexity of the generation of the linear block code, the solution is that sorry. So this thing is mentioned that if K is large, a table lookup implementation of the encoder becomes prohibited. So too high lookup table, or this is very difficult to store. Suppose the 92 message bit, and you are adding redundancy, and it is generate 127. So 2 to the power 92 message sequence you have to be stored, and along with its code word. So 2 to the power 92 code word you have to be stored. So it is very difficult for storing these things. That's why, what should be the solution? The solution is the basis function, basis vector. Solution is the basis vector. So to overcome these things, or to get rid of storing such large number of your code word, we generate the code word by means of some basis vector, and this basis vector will be form a generator matrix, and by using the generator matrix we can design the code word, any code word for any message sequence. So the solution is, it is possible to generate code vectors using some basis vector instead of storing large lookup table. Okay. Now, it is possible to find a set of k linearly independent n tuple v1, v2 up to vk on the basis of the subspace. So, how many n tuple are there? There are n tuple is v1, v2 up to vn, but your message vector is your k. So there is k tuples message vector are there, v1, v2 up to vk. So the v1, v2, v3 up to vk will be mapped into v1, v2, v2 up to vk from the vn, your vector space. Since each n tuple of the subspace is a linear combination of v1, v2 and vk, the code word that is generated u will be m1 into v1, m2 into v2 and mk into vk. So what does it mean? So it is saying that if I consider the three number of message vectors are there, three number of message bits are there. In each packet contain three number of your message digit. Okay, so only this three, if we store only the three vector, linearly independent three vector, and these three vectors are called the basis of the subspace, these three vectors will be generate the whole code word, the 8 code word. So no need to store 8 code word. Only you store the 3 code word, because your message digit is 3. So instead of storing 2 to the power 3 equal to 8 code word in the lookup table, we store only 3 basis vector, and these 3 basis vector, by using these 3 basis vector, you can generate rest of the code word vector. Okay. So how it can be possible? So since each n tuple of the subspace is a linear combination of v1, v2 and vk, so code word can be generated. m1 has message bit into the basis vector v1, m2 basis vector v2, this is the linear combination up to mk into vk. If I say the message bit is 3, so your basis vector will be v1, v2 and v3. So your v1 will be multiplied with the message bit m1, v2 will be multiplied with the message bit m2, and v3 will be multiplied with the message bit v3, and the addition of that, summation of that, will give a code word sequence. So for 6-3 code, 3 k equal to 3 basis vector are needed to generate the 8 code word vector. So only you have to be store 3 code word, 3 basis vector instead of storing the 8 code word vector in the lookup table. And this basis vector form the generator matrix. And one thing is very important, these basis vectors are linearly independent. Linearly independent means, in previous case, we have considered that summation of the two codeword vector gives a valid codeword vector within that code. But here, if I say V1, V2 and V3, this V1, V2 and V3, three are the basis vector. So addition of V1 and V2 should not give the result such that it is equal to V3, or V1 and V3 will not result that equal to V2. So all are linearly independent. They should be linearly independent. And by using this basis vector, we are generating, they form a generator matrix. As we are considering Vk message bits, k number of message bits, so basis vector are V1, V2 and Vk, and this will be like that, V11, V12, like this k cross n generator matrix we are generating by using the basis vector. The 2 to the power k code vector can be described by a set of k linearly independent code vector. This thing I have already mentioned. Now, if m is equal to m1, m2, these are the message bits or digit. Each packet contains k number of message digit. Then how you generate the code vector for any of the message? That code vector u equal to m into g. G is this g. V1, V2 and Vk. Your message is m1, m2 up to mk multiplied with V1, V2 and Vk. So now your problem is solved, that storage space is not required that much, weight is reduced and also complexity is reduced, and encoder need to store only k rows of G instead of 2 to the power k code vector of the code. So you are relaxing, so your storage is reduced and encoder need to store the k rows of G. G means generator matrix instead of 2 to the power k code vector of the code. Now G is V1, V2 and V3 for 6-3 message vector. I am considering 6-3 code. 6-3 block code. 3 is the message bit and 3 is your redundant bit is added. So code length is 6. So A is 6, K is equal to 3. And we are considering a V1 is of this form 1 1 0 1 0 0 0 1 1 0 1 0 1 0 1 0 0 1. So how we are choosing this thing? This is nothing but we have chosen from this 2 to the power 3, that means 8 code word. So from the 8 code word, only 3 we are choosing, and these 3 should be linearly independent. They are basis vector. They are linearly independent. So these 3 basis vector, if we sum or add, the resultant is not gives another basis vector. Okay, so they are linearly independent. So that's why we are choosing this thing. And we are considering a message is m equal to 110. So first you observe here for 110, what is your code word generated? 101110. So 101110. So 1 0 1 1 1 0. Okay. So now there is no lookup table. Only the table contains 3 basis vector. What are the basis vector? Basis vector is 1 1 0 0 1 1 and 1 0 1 and 1 0 0 0 1 0 0 0 1. See, this is, if I consider, so this is a, just a diagonal matrix. So this is a diagonal matrix. So for this message, using this generator matrix, you can generate the code word. So we are using a 1 1 0 multiplied with V1 V2 V3. So V1 V2 V3 means this thing. So 1 is multiplied with V1, 1 will be, next one is multiplied with V2, 0 will be multiplied with V3. So 1 multiplied with V1 means 1 1 0 1 0 0. Next is 1 multiplied with 0 1 1 0 1 0. Next 0 is multiplied with 1 0 1 0 0 1. Clear? So after multiplication, what you are getting? So this will be your 0, but this 1 is multiplied, this thing means same, and this will be, gives you same. Now you add this thing, 1 and 0, that is 1. 1 multiplied with 1, 0. 0 multiplied with 1, that is 1. 1 multiplied with 0, that is also 1. 0 multiplied with 1, that is also 1. 0 is multiplied with, sorry, not multiplication, 0 is added with 0, that is also 0. So this XOR operation or modulo 2 operation, you are the generate 1 0 1 1 1 0. So that is 1 0 1 1 0. So this thing is same as the lookup table is given 1 0 1 1 0. So any of the message vector 1 1 1 you can easily generate by using this generator matrix. Okay. So only using the, so this your for 1 1 for 1 1 0, this is the code what you are generating. And see, in this case, this message 1 1 0 is also contained here 1 1 0 1 1 0. So 1 0 1, oh sorry, so your 1 0 1 is just the parity bit is added. 1 0 1 is the parity bit added, and 1 1 1 is your message bit. Okay, so this is the redundant bit n minus k, and this is your message bit. Thus, the code vector corresponding to a message vector is a linear combination of the rows of G. The message vector is nothing but how you are generating. This is nothing but the linear combination. This is linear combination. So since it is totally defined by G, the encoder need only to store k rows of G instead of 2 to the power k vector of the code. That is already number of time I have mentioned. So this is the systematic linear code, because you can easily identify which one is the parity bit and which one is your message. But in case of non-systematic, parity bit can be added anywhere in the message bits. Okay, so it is very difficult. This design is complex and difficult to identify. So obviously, the efficiency of non-systematic is much more compared to the systematic addition of the message bit. The systematic addition of the redundant bit in case of your linear block code. Now, a systematic NK linear block code is mapping from k-dimensional message vector to a n-dimensional code vector. So n-dimensional code word we are transforming from k-dimensional message vector. So this was your message is transformed into n-dimensional space, and n minus k redundant digit is appended with the message bit. Why we are appending? Because to combat error that is introducing during transmission of the information through the channel. So we can represent that this thing here, this generator matrix. In the generator matrix, see here 1 1 0 0 1 1 1 1 1. Sorry, 1 0 1, and the last three. This is the all the diagonal element is 1. So this is the I matrix. So if I write G as this is parity matrix and this is your I matrix, so we can represent that systematic addition or systematic linear block code. Generator matrix generation is very simple. This will be the parity, and the rest will be the your that is IK, means your identity matrix. So it will be looks like that. It can be generated this way: P11, P12, P21. Similarly, K number of message bits. So PK12, PK n minus K, and this will be gives you your n minus K means your it is your parity bit dimension, because n minus K is your redundant bit. This much of redundant bits you are adding, and this is your the I matrix. So the generation of the generator matrix is very easy in case of systematic linear block code. So this systematic generator matrix, the encoding complexity further is reduced. One is reduced by the that is the by means of the basis function. Also further is reduced by means of this thing. So no need to store this thing. Only you are storing the parity matrix. Okay. So storing space also be again further reduced. Now systematic linear block code, if I consider that message bit M, message vector or message M, that is message vector M, contain k number of bits, code vector U contain n number of your bits, and after coding this is, so systematic code means first is your parity bit and then is your message bit. So systematic code word are sometimes written so that the message bit occupied the left hand portion. Here I am saying that the message bit is right hand portion of the code word and parity bit occupies the right hand. But here we are considering left is parity and right is message. This reordering has no effect in error detection or error correction properties of the code. Now in this case we are showing same thing, same 6-3 code, and we are considering that how your that is the parity bit is the parity bit is nothing but linear combination of your message bit. Parity bit is nothing but your linear combination of the message bit. So the generation of the parity bit is also be very easy. It is, you can generate the parity bit. It is nothing but the linear combination of the message bit. So we are considering same 6-3 linear block code, and we are considering a that is a code word. And what is this thing? So this is actually nothing but your generator matrix. Okay, this is generator matrix that we have chosen here. This generator matrix 1 1 0 1 0 0. This thing. So 1 1 0. See here. 1 1 0 1 0 0. Next one is 0 1 1 0 1 0. 0 1 1 0 1 0. Third one is 1 0 1 0 0 1. Okay, 1 0 1 1 0 1 0 0 1. So this is your I matrix and this is the parity matrix. So code is generated by the message bit, 3 message bit M1, M2 and M3 with the generator matrix. This is the generator matrix, nothing but I am showing here like this because this is P and this is I. Actually this should be just a line. Okay. So this how it is added, the see here, that is the, if I just multiply this thing row and column wise, first is M1 and M3, M1 plus M3. Next one is your M1 plus M2. So this is showing M1 plus M2. Third is your, that is your M2 plus M3. So M2 plus M3. Just your matrix multiplication. I am doing matrix multiplication. Again is last 3 is M1. Next is M2 and M3. So we are multiplying this row and the column of this generator matrix. So it will be gives you M1 plus M2, M1 plus M1 plus M3, M1 plus M2, M2 plus M3 and M1, M2, M3. So M1, M2, M3. So this U, so M1, M2, M3 are the message bits. So that message bits will be converted into n number of 3 message bit is converted into 6 digit when it is transformed into code word. So transform into code word is U1, U2, U3, U4, U5 and U6. So see here 6 here and your message was 3. Now out of these 6, last 3 are same as M1, M2, M3, this message bit. So the first U1, U2, U3, these are nothing but your parity bit. You are adding 3 redundant bit. This is your original message and this is the parity bit you are adding. So what is U1? U1 is M1 plus M3. So the parity bit, if I say this is P1 parity bit, this P1 parity bit is generated by the linear combination of message M1 and M3. Similarly U2 and M3. So the parity bit generation is very easy. So this is nothing but the linear combination of the message digit or message bits. So this equation provides some insight into the structure of the linear block. Redundant digits are produced in a variety of ways. Parity bit here, P1 is M1 plus M3. This is wrong actually, M1 plus M3. It should be M1 plus M3. M2, P2 is M1 plus M2 and P3 is M2 plus M3. So very simple way you can generate. So up to this, so this code word, you are converting message M1, M2, M3, transform into U1, U2, U3, U4, U5 and U6. So your code is generated. Now this coded information you are transmitting through the channel. So your information is modified. How it is modified? By redundant bits. So length of the message is increases. Length of the message is increases. So when you retrieve the information at the receiver section or recover the information at the receiver section, you have to remove the redundant bits to extract your actual message. Okay. So how you can get back the original message? if is there any error or not within your received vector, how can you detect that thing? So this will be, for this case, we have to be consider the parity checker matrix or parity check matrix or parity checker. And generally, we are denoting generator matrix by G and parity check matrix by H. And G matrix and H matrix, they are orthogonal. Okay, G matrix and the H matrix, they are orthogonal. So G and H, that is the rows of G, are orthogonal to the rows of H. That means G H transpose is equal to 0. G H transpose is equal to 0. So it will be, so this U is a code word generated by G, and this should be possible. That means if I consider that for each generator matrix there exists a parity check matrix, and this parity check matrix is G H transpose should be equal to 0. So obviously this code word U is also generated from G, so U H transpose should also be 0. So U is a code word generated by the G matrix G, so you can check is this U is generated from the generator matrix or not. How can you check? Because we know that the rows of G are orthogonal to the rows of H, parity check matrix. So G H transpose equal to 0 as they are orthogonal. So obviously as U is generated from G matrix, so UH transpose should also be 0. If UH transpose is not 0, so obviously U is not generated from the G matrix or some error is occurs. So parity check matrix H will enable us to decode the received vector. So using these properties or using this your condition, so you can check whether there is an error or not, and this is called the syndrome calculation. Okay, syndrome. Syndrome is used to check whether there is an error within the message, received message or not. So in a systematic code with G, that is a parity matrix and then the I matrix, and as G and H are orthogonal, rows of G and H are orthogonal, so obviously H will be first is your I matrix, then P transpose matrix. Okay, because they are orthogonal, so obviously this will be rows transformed into column. We know that that at the receiver we are receiving the vector R. If I receive the vector R, so R should be the code word vector U and the linear sum of the error vector. If E is equal to 0, so obviously R is equal to U. Okay, so how can we check is there any error or not? That is by using syndrome calculation. Syndrome of R used for error detection and the correction. If we locate the error, if we detect the error or locate the error, error correction is very simple because it is binary operation. So your digit are 1 and 0. So obviously the some error when occur. So 1 is just due to error is that means converted into 0, or 0 is converted into 1. So if error is detected and position of the error is detected, just you flip the bit, you can easily correct the error. So the syndrome S is denoted the syndrome. S is RH transpose. Here R is your receive vector. So within the R there is U and E. So if RH transpose, because H is your parity check matrix, so we are operating H matrix on R. Okay, and R is your U, so U plus E, and the U is nothing but generated from capital G, generator matrix. So GH transpose, so if GH transpose is 0 or RH transpose is 0, that means no error. So you are detecting the code, received code word is correct code word. So this is the valid code word you have received. And if it is not 0, that means there is some error. Clear? So we are S is equal to your RH transpose. So this is replacing U plus E. So U plus E H transpose. So UH transpose, EH transpose. So what is UH transpose? U is G. U is generated from G. So obviously this is GH transpose. So GH transpose must be 0 because of orthogonality property. So UH transpose should be 0. So for all member of the code word cell. So what you are getting S equal to EH transpose. So this is very important for syndrome testing. EH transpose is very important for syndrome testing. An important property of linear block codes fundamental to the decoding process is that mapping between correctable error pattern and the syndrome is 1-to-1. Okay, this is 1-to-1 your mapping for your correctable error pattern and the syndrome. So this will be clear if I take an example. Now, two important properties of the parity check matrix. So parity check matrix, no column of H matrix can be all 0. In previous case, what we have considered, that the code vector should contain all the 0 vector, but not for the generator matrix vector. Generator matrix vector is generated from the basis vector. Similarly, the H vector should not contain the all 0 vector. Otherwise, the error detection is not possible. Otherwise, error pattern would not affect the syndrome and error would be undetectable. And all column of H must be unique. Otherwise, error position would be indistinguishable. Okay. So to determine the error position, so all the columns of the H should be unique and should not contain any column that all 0. This should be very important thing. Now take an example for syndrome testing. We are considering that code vector U 101110 is transmitted and receive vector is 001110. So you can easily observe from that there is an error. Okay, but receiver don't know what is U. Receiver only receive R. That is this thing, that error. Now from the syndrome calculation, we have to be check the error is there or not. So S is, we know, RH transpose. So we know that we have already generated the G vector generator matrix from the 3 basis vector. So that is 1 1 0 0 1 1 1 0 1, and this is the I matrix. So H matrix will be, that will be this part will be your first part will be I matrix, and this will be P transpose matrix. So I matrix same 1 0 0 0 1 0, this is the only diagonal element, and P transpose. So P transpose means 1 0 1, that is 1 0 1. Next is 1 1 1. Next is 1 1 0. and third one is 0 1 1. So 0 1 1. Okay, so this column of G transpose into rows of H matrix. Clear? Now we are considering the S. S is RH transpose, and that is equal to UH transpose. Why we are considering UH transpose? Because R is nothing but your that is your generated from the transmitted symbol U. So we are considering we are testing here. If we test the UH transpose, U is that is formed from the generator matrix. So it gives you that is 0 0 0. So what is U? U is 1 0 1 1 1 0. 1 0 1 1 1 0 multiplied with H transpose. This is H, and if you transform it, so it will be 1 0 0 1 0 0, then 0 1 0 0 1 0 0 0 1 0 0 1. Next is 1 0 1 1. Sorry, this is the transpose. Sorry, this is transpose. So this will be rows will be columns. So 1 0 0 1 0 1 1 0 0 1 0 1. Next is 0 1 0 1 1 0 0 1 0 1 1 0. Last is 0 0 1 0 1 1 0 0 1 0 1 1. Okay. So it is tested that it is okay. So this is only for showing testing that is it okay or not. But actually receiver will not check this thing. Receiver will be check this thing. So what is receiver receive? Receiver receive are 0 0 1 1 1 0. Okay, and H transpose is this thing. So when receiver check this thing after calculation, it gives 1 0 0. So previously it is 0 0 0, means if at the transmitter section if it is checked, then no error, but after transmission, when receiver check, receiver found that your syndrome is non-zero. Okay, so that means some error is occurs. Now how to correct the error? So you have to be locate the error, or you have to find out the position of the error. How we can find out the position of error? Very simple. To find out the position of the error, see here, one thing is very important. To find the error, that 1 0 0, we have observed that in this case 1 0 0. This 1 0 0 is which position of the bits, receive bits is error. You can easily find out. You have to find out 1 0 0 is where in the H transpose matrix. 1 0 0. 1 0 0 is the first row of the H transpose matrix. If suppose error is 0 1 0, then 0 1 0 is the second row of the transpose matrix, H transpose matrix. If suppose this is happened 1 0 1, so 1 0 1 is your the last row. Okay, so last row. So as in this case we have found 1 0 0, so this is the first row of the H transpose matrix. So you can easily easily locate the error that it is the first bit position of the receive vector. Okay, and in this case how many message bits? 1 2 3 5 2 1 2 3 4 5 6 6 message vector. So error position will also be 6. So your error position E1 E2 E3 E4 E5 E6. This is wrong. This should be 6 1 0 0. So here this 6 is written. Okay, so 1 0 0 0 0 1. So that means the first position of your H matrix, there is an error. So the first bit of the error vector, there is an error. If we add this thing with your receive vector, so you can easily recover the bit, that means easily you correct the bit, or you just flip that bit. So you can easily correct that thing. So detected a single error, you can correct such error, locate the error position by syndrome testing, then reversing the bit, we can get corrected what, as the system is a binary system. Up to this thing is clear to you? Hello, this thing is clear to you?
Yes, ma'am.
Yes, ma'am.
So this is another example is showing. So you can easily calculate this thing. This is for your homework assignment. Okay. And this is what thing is given. This is also 6-3 code word. Generator matrix is also given. And DC word is this thing. You have to find out the transmitted information. Okay. If this is received, so what will be the U? What should be the U? So you have to find out that thing. So from the syndrome calculation, you can easily find out your, that is R is given. R is given. From G, you can easily find out your H. So that is also be shown. And your syndrome you can easily calculate it because R is received, H transfer. Now you don't know this received R is your actually erroneous received word or correct code word. So by syndrome testing you have to check that thing. And for syndrome testing, it is find out that is it is non-zero. So it is erroneous code word that is received. So 110. Now is 110 the location of the error bit where? So you have to find out which rows of this thing, which then it will be 110. 110 is this is the third. This is the third, isn't it? So if you flip the receive bit, the third receive bit, so your third receive bit means this one. If you flip this thing, so it will be correct you. Otherwise, you have to be add the 001 000 with receive code word that you have received, that is 100011. Okay. So this thing, this thing is given here, so you can easily go through this, so and can easily generate the correct. You can easily obtain the transmitted code word. So this thing already I have mentioned, so no need to again just read out this thing. Only you calculate for decoding, you calculate the syndrome, then locate the error position. This error pattern assumed to be corrupted by the channel, and then you correct the error by adding the receive vector with the error pattern, and you can easily retrieve the correct code word or easily correct the code word. Now in case of your decoder implementation, decoder follow the 3 rules. One is first calculate syndrome calculation, then locate the error pattern, then perform modulo 2 addition of error pattern with the receive vector. Okay. This is your for decoder implementation. You can design the decoder hardware based or can design software based. So if it is a software based, so obviously you have to be algorithm, you have to generate the algorithm. So in the algorithm, so you have to be first calculate the syndrome, then find out the location of the error or locate the error pattern, then you just linear addition of the received vector with the error pattern, you can easily correct the error. And in hardware, this can be implemented by exclusive OR gate and AND gate to perform any single error pattern. Here, we can only correct the single error pattern. Okay. By this technique, we can correct the single error pattern. So this circuit, that means already mentioned, the circuit made up of exclusive OR gate and AND gate to perform a single error, to perform any single error pattern of this syndrome calculation. So these things, syndrome calculation is showing. In this case, 3 syndrome we are considering, because in our case 6-3 code, and always we are considering here 3 syndrome is 3, 110 or 100 like that. So S1, S2, S3, and receive code vector 6 code word length. So R1, R2, R3, R4, R5, and R6. And S1, S2, S3, they are generated as the modulo operation of the receive code word vector. Now, which receive bits, these are the bits, which receive bits are added, that will be follow that in this case. That means S is your, this is your H matrix, this is H transpose matrix. So your first syndrome S1 will be, that is the R1, then your R4, then R6, and the second syndrome, that will be R2, then R4, then R5, and the third syndrome is, that is your R3, R5, and R6. So this way, R1, R4, and R6. See here, first one R1, R4, and R6 is added. Similarly this way, and based on that your error pattern is generated. So exclusive OR operation. After that, your error pattern is generated, and this error pattern again added with the receive vector, forward vector, whether it is erroneous or correct forward. If it is erroneous, obviously either E1 or E2 or E3 or E4, any one of that will be non-zero. And when it is added, exclusive or added, you are getting back the correct forward. So this way you can easily implement it in hardware. Okay. So this thing already I have mentioned, and this is for simple operations, so that's why very simple circuit you can easily design, but for large length of code, so it is very difficult to handle or difficult to manage. So this is one assignment is given to you, that is a 7-4 code, that means 4 message bits. After adding 3 redundant bits, length of the code is 7. So H matrix is given, parity check matrix is given, and U is also be, this is transmitted code word is given, and this is your receive code word. So you have to be calculate the syndrome. You have to be calculate the syndrome. Okay, very simple. It's very easy way you can calculate the syndrome. Just R H transpose. If we consider R H transpose, you can easily find out the syndrome, and from the syndrome you can find out the error pattern and add with R. If we add with R, does it give the same U or not, you can easily find out. So up to this thing, yes, your today's class, Okay. I think from the next class, we'll be meeting the online and offline mode. If possible, I will take the Monday class. Okay, so I will inform you if it is possible, because Monday is your university holiday. Okay, so I may take class on Monday. Let me check my schedule. So I will be informed you. I will inform within your Saturday. Okay. So only for 13 are joining today's class. Why? All are not informed? Tuhin, all are not informed?
I have informed all.
So Tuhin is present, Suchanda present, Abhishek, Mollik present, Viprojit present, Sudip present, Oindila present, Bobita is also present, Aditi, Surojit, Musraf. Any other?
I'm Oshit Das.
Oshit. And?
Madam Shudipto here.
Huh?
Shudipto Pal.
Any other? It should be 13. 13 means 12 from MTech, 1 is PhD candidate. So who is the 12th candidate?
এক্সকিউজ মি ম্যাডাম,
হ্যাঁ
16 তারিখ থেকে কি অফলাইন ক্লাস চালু হবে?
16 তারিখ থেকে তো হওয়ার কথা, এখন তো বুঝতে পারছি না। এখনো পর্যন্ত জানি 16 তারিখে হবে, তবে 12th নভেম্বর মিনস কালকে, তো টুমোরো
হ্যাঁ,
একটা মিটিং আছে, সেই মিটিং এর পরে বলতে পারবো যে হবে কি হবে না। এখনো পর্যন্ত আমাদের কাছে যা আছে কিন্তু হবে না। কে বলছো তুমি, বলো।
আমি তুহিন বললাম।
আচ্ছা, কে গো? আর একজনের নাম তো পাচ্ছি না। বিপ্রজিৎ দিয়েছি গো। ও, বিপ্রজিৎ দুটো অ্যাকাউন্ট থেকে জয়েন করছো, তার মানে তোমরা 13। আর সুদীপ্ত হচ্ছে তোমার পিএইচডি ক্যান্ডিডেট। Okay, so for today's that's are all. So thank you all. So on Monday we may again meet, but একটা জিনিস তোমরা একটু করবে, যে সমস্যা যেটা হচ্ছে যে হয়তো আমি দিয়ে দিচ্ছি, তারপরে অন্য টিচার দিয়ে দিচ্ছে, একটু বলে নেবে স্যারকে, নাহলে অসুবিধা হবে। কারণ আমি একটু আগে থেকেই ওই জন্য বলে রেখেছিলাম। তোমাদের কি আজকে শিডিউল ক্লাস ছিল? হেডের কি ছিল শিডিউল ক্লাস?
2:30 তে ম্যাম।
2:30 তে। যাই হোক, এরপর থেকে একটু জাস্ট বলে নিও। শুনে স্যাররা হয়তো জানেন না, হয়তো ফাঁকা আছেন বলে নিয়ে নিচ্ছেন, যেমন আমি তোমাদেরকে বলে রেখেছিলাম। যেমন একটু স্যারকে তাহলে বলে রাখবেন যে আমাদের অলরেডি অ্যাসাইন ক্লাস হয়ে রয়েছে। ঠিক আছে, ওকে, থ্যাংক ইউ।
ওকে ম্যাম, থ্যাংক ইউ।
Thank you, madam.
Thank you.
থ্যাংক ইউ ম্যাম।
Okay, thank you all.